So I'm Dan, and today I'd like to present some work that I've done with colleagues Marco, Stefan, and Anya, looking at basically trying to understand how to reap the benefits of partial SDN deployment in enterprise networks. So in other words, trying to understand the incremental deployment case for software-defined networking. So is there anybody here that wants or needs a sort of intro to SDN? I would assume that everybody is pretty familiar with it, given that we're in Berkeley, kind of the heart of SDN. But okay, cool. All right, so Berkeley's a pretty systems strong place, so imagine that you are a network operator and this is your enterprise network. You face a lot of challenges as the network operator with this network. So you have to deal with complex policy changes, so access control list updates, maintaining isolation boundaries between different parts of the network. You have to deal with heterogeneity, so lots of different devices in the network expose different interfaces for managing and controlling the traffic. Allocating resources for different groups of traffic is quite a challenge because you don't necessarily know when you're going to need what resources in the network. Scheduled maintenance is a real problem, especially in enterprise networks, although you can argue it's a problem in all networks, where there's no nice programmatic way to be able to express that I want to take a part of the network down and out and simply allow the traffic to, route around in an elegant way. You actually have to go and deal with low-level configuration primitives to basically prevent disruptions. Device lifecycle management is a big deal for enterprise networks because they try to maintain very homogeneous devices and even specific device types from specific vendors. And this leads to problems with lifecycle. And finally, troubleshooting is a generic problem in networks of all kinds, especially in the enterprise, due to the lack of powerful troubleshooting tools in conventional enterprise network hardware. These all add up to basically make for a very complex set of operational challenges in enterprise networks. So one potential avenue to sort of attacking these challenges has been proposed through software-defined networking. And software-defined networking, as I'm sure you all know, is a way to separate the control from the forwarding mechanism of the network and basically leverage abstraction. So be able to think about the configuration as, prominent researcher from this group says, as a function over a graph. And there's been a lot of research in the SDN community toward trying to make use and leverage these abstractions. So from last year's SIGCOMM, there was a paper on abstractions for network update that showed how to get something called per packet consistency in a network update, where a packet traversing the network is only handled according to the first configuration or the state after the update, but never a mixture of two policies, which is something that's very hard to achieve in conventional networking. There's been some work showing how you can build up complex policy enforcement mechanisms from modules from people in the programming languages community. There's been a lot of work that shows how you can actually reason about the static forwarding state of your network and check for invariance. For example, can hosts from network A communicate with hosts from network B? And there's been a lot of work recently as well trying to do automated and rich network troubleshooting. But the problem is that all of these approaches leverage an existing SDN deployment. So if you don't have SDN in your network today, it's very hard to actually take advantage of these. So let's go back and look at this topology description of a large-scale campus enterprise network. And in order to actually get SDN into the network today, the only option is to do a full upgrade, sort of a forklift type overhaul of your network. And for an enterprise network, this is simply infeasible because of budget constraints and simply the intractability of throwing out all your network infrastructure. So we call this the SDN deployment problem. And it necessitates that in order to get SDN into the network, it must be introduced in an incremental fashion. So this is like the predicate of our problem statement. So given that reality of the need for incremental deployment, we want to ask two key questions. So how can we incrementally deploy SDN into existing enterprise networks? And is it possible to actually reap the benefits of SDN given just a partial deployment? So let's look at the very first question and sort of take a step backwards to look at how current transitional networks actually look. And when I say transitional, I mean networks consisting of SDN-capable devices and legacy devices. So the first mode of operation that's been proposed is what's called a dual stack approach, where devices in the network are upgraded to support both a kind of either SDN functionality along with a legacy functionality. So you might think of a MAC learning switch that also supports open flow rules, and you can carve out traffic to be handled by one or the other. But this particular model does not necessarily address in itself the question of how do you operate a network like this as an SDN. It requires you to make a choice about what parts of the traffic you're going to handle through the legacy management interface and what you're going to handle through the SDN. Another approach, slightly more recently proposed and very popular in commercial data centers, is to think about SDN deployment just at the edge of the network and make use of whatever existing sort of legacy network management protocols and interfaces exist, whether that's ECMP using some routing protocol. But the problem is that in the data center environment, it's very easy to deploy this in the form of, for example, a software switch in the hypervisor. But if we look at the enterprise network, we're dealing with an edge of the network that comprises potentially thousands of legacy hardware devices. And to upgrade all of these devices to basically get SDN at the edge is about as intractable as doing the entire network. So we need to think about how to do this differently. And this brings me to Panopticon. So Panopticon is both an architecture that enables an operator to run a network as a nearly fully SDN, as well as a planning tool that allows us to determine how to deploy SDN functionality into the existing enterprise network. And I'll show you what I mean by that by going through sort of an outline of the rest of this talk. So I'm going to go and describe a little bit about what the Panopticon architecture is. Then I'm going to talk about the cost optimization framework, so the planning tool that we use to decide how to upgrade and integrate SDN devices into the existing legacy network. And then I'm going to give an overview of the evaluation that we ran over a real enterprise network with packet level traces and show you how SDN actually works out. So I'm going to jump next into the architecture. So let's have a look at this very simplistic representation of an enterprise network. Panopticon can reason about both layer 2 and layer 3 devices. But for the sake of simplicity in this talk, let's just reason about this as a layer 2 Ethernet network that's running a spanning tree protocol. So the first thing that we need to do is we need to figure out how to plan the deployment. So you might envision that the network operator comes to you and says, I have the following endpoints in the network. And these might be host-facing endpoints from access switches or switch ports on distribution switches that face access switches, depending upon the level of granularity of control that's needed. And they will designate which ports must be controlled through the SDN programming interface and which can be potentially left as best effort. Now, given that information about the network topology, we're going to feed that into our cost-aware optimization tool, along with a set of traffic estimates, which we take from maybe packet-level measurements of the topology. We're going to take a set of objectives, which are going to include things like the upgrade budget, just how much cash we have to spend on getting sort of a first shot of SDN into the network, as well as things like path delay, how much additional stretch or number of hops we're willing to let packets traverse in our network, as well as a bunch of tunable parameters that we get to decide. So for example, priorities of the switch ports, the price model, and thresholds for utilization of the network. So what link capacities we're willing to tolerate, the number of VLANs we assume to be supported in the legacy network, and so on. And that's going to run on these inputs and spit out basically a plan for how to deploy which devices into the network. In other words, an optimized partial SDN deployment. So let's return back to the network and let's imagine that these are the two switches or routers that our tool decides we should upgrade to get SDN, an SDN abstraction of our network. Now, the first question, returning to our key questions, we want to ask, what is the benefit of partial deployment in this particular network? And the first observation you might make is that having these SDN programmable devices in the network allows us to harvest previously unutilized network capacity in the form of going around the sort of inefficient mechanisms of spanning tree protocol and harvesting those link resources. But it turns out that actually we believe there's a much stronger benefit of SDN, and that is namely that it enables the principled orchestration of the network policy. And when I say network policy, I mean a high-level, potentially declarative sort of set of instructions that the network is supposed to abide its packet forwarding according to. So what do we mean? So actually, let me step back. So the question that we want to ask, again, is can a partial SDN deployment still take advantage of the principled network orchestration that we've seen in these academic research papers that all leverage a full SDN deployment? So to answer this question, we're going to leverage two key insights. So the first key insight is that for any path between a source and destination ingress point, or we just call them endpoints in the network, A and F, that traverses at least one SDN programmable switch, this gives us the ability to achieve end-to-end policy enforcement. And this might take the form of implementing an access control mechanism or redirecting traffic to some kind of intrusion detection middle box or other type of middle box. The second insight is that for all traffic that traverses at least two SDN programmable switches, we can achieve finer grained control over the traffic. We can actually do load balancing, for example, the form of traffic engineering over the paths that exist between the SDN upgraded switches. And I should actually take a moment to say if there's anything unclear or if you have any questions, please go ahead and ask, just to make sure that we're all on the same page. Okay, so given these two insights, these require that we are capable of ensuring all traffic from every SDN controlled endpoint traverses at least one SDN switch. And we call this the SDN Waypoint Enforcement principle. And to achieve this waypoint enforcement, we must force legacy devices to direct traffic to SDN switches so that legacy devices cannot simply curtail or shortcut the SDN policy enforcing switches. So let's just look at a simple straw man solution for how we might do this. So let's pick an origin ingress port A, and we'll choose a designated SDN switch for every destination from A in the network. And then we would assign a VLAN, a unique VLAN ID, to each path from A. But as you see, I mean, as it's probably obvious, this particular solution does not scale. It's impractical for a number of reasons. The key one is that VLAN ID space simply cannot scale to handle the entire network in this fashion. So let me describe how Panopticon solves this problem. So the first thing that we do is we conceptually group endpoints in the network into what we call cell blocks. And these are connected components that you get when you basically remove the SDN upgraded switches from the network. And it's a conceptual grouping that allows us to more easily reason about the scalability properties of the network. Within each one of the cell blocks, we build a mechanism that we call solitary confinement trees. And these are per port spanning trees that ensure waypoint enforcement between every endpoint and the programmable SDN switches. So for example, for B to be able to communicate with C, the traffic would have to traverse B's solitary confinement tree to the upgraded switch and then return back towards C. And this would allow us to achieve the benefits that we described when we get waypoint enforcement. So this is basically the way that we do it. We take each endpoint and we assign one unique VLAN ID per ingress point per cell block, excuse me. We can reuse VLAN IDs across the different cell blocks to improve the scalability of the system. And these solitary confinement tree, if they're implemented with VLANs, they can actually be pre-installed at the time of network design, or network deployment, I should say. All right. There's one more aspect to the architecture, which is the interswitch mesh. Now, the interswitch mesh is what we call the set of paths that can be used between any pair of SDN-capable devices in the network. And this allows us to leverage path diversity, for example, to balance traffic over available paths, or for any other reason that we might want to steer traffic at finer levels of granularity. All right, so let's look at where we are now. So now that we have the SDN Waypoint Enforcement mechanism, this allows us to have Panopticon abstract the physical topology to a logical SDN, which we then expose to the SDN platform. And so essentially what Panopticon does is it provides the abstraction of a nearly fully deployed SDN whose resolution, or you could say, there's a word I'm looking for, fidelity. The fidelity of the view of the network increases as more and more switches and routers get upgraded to support SDN. So this is the basic principle of the Panopticon architecture. So what control does Panopticon actually give you over the traffic in the network? So we reasoned that there are kind of two classes of policy declarations. The first type is what we would call end-to-end, the kind of policy that you could express if your network were just one huge switch. For example, dynamic filtering of traffic or middle box redirection. The other type, and I should mention that this type of control is like the key benefit that we can show that you get with Panopticon. The second kind is a little bit more tricky, and that is namely the routing policy, because this depends, it's a function of the upgraded network in a sense. So the ability to do balancing of traffic over paths essentially reduces to a function of how much of the network you've upgraded, as well as the network topology and other factors. Okay, so I've gone through the network architecture of Panopticon. Next, I'm going to dive into the cost-aware optimization framework, so how we actually do the choice of what switches to upgrade. So you'll remember that I showed this slide that has all of the inputs and the parameters that we get to choose, and it spits out a set of switches that we want to upgrade. So let me go into what the constraints and objectives actually are. So the first constraint that we deal with is the number of VLANs that are actually supported in the legacy network. And this dictates basically how many endpoints we can have in a cell block, because we need these in order to separate traffic and force or actually let me say, we need them to be able to realize the SDN Waypoint Enforcement policy. The second is naturally the capacity of the SDN switches, the flow table capacity. How many source destination pairs and specific fine-grained policies can we actually realize as a function of the number of entries in a flow table? And at the same time, subject to these constraints, we want to minimize the path stretch, so the number of additional hops traffic has to traverse in order to actually be subject to the SDN Waypoint Enforcement policy. We want to minimize the cost of the upgrade. And to this end, we actually use a cost model that describes the cost of an upgraded switch as a function of the port density, the line speed, the number of flow table entries that are supported, and other parameters like that. Now you'll recall that the admin would come to the network designer with a list of endpoints that are to be controlled through the SDN interface, as well as a set of endpoints that might be considered to be best effort, in the sense that we want to control these endpoints through the SDN programming interface if there's sufficient capacity in the network to do so. And so these basically are the objectives and constraints. And you can think about this as like a cost optimization problem. You can either choose to minimize the cost subject to a threshold on the maximum allowed path stretch, or you can spin it and you can minimize the maximum path stretch subject to a budget threshold. So there are different ways that you can reason about this, this optimization problem.
Does path stretch incorporate the loss you'll get in regard to load balancing?
So the metric that we chose does not, but you very easily could. Yeah. Sorry.
Where does the bandwidth come into play?
So I will get to the traffic model in the evaluation section, but definitely The additional constraints beyond the ones on this slide include the link capacity that you have to deal with, and the traffic estimates that you measure in the network are going to give you sort of a frame of reference to reason about whether or not you're actually oversubscribing a link. Like, you might imagine that along this particular physical link, since you have packets that are traversing, in the case where they would not traverse without the SDN Waypoint Enforcement, you're going to be increasing the utilization of the links in the network. So we do reason about that, and I'll get to that a little bit later in the talk. But you're absolutely right. Those are certainly constraints that we need to work into our model. Okay, so we've taken these constraints and objectives, and including the constraints that you mentioned about link capacity and the traffic model, and we formulated out of these an optimization problem that gives us an optimal sort of embedding of SDN switches, the set of switches or routers that we should upgrade. But the complexity, the runtime complexity of this optimization problem is NP hard. And therefore, one of the challenges we faced was to develop greedy heuristics that let us approximate the solutions to the problem. So I'm going to give you an overview of the two heuristics that we use in our evaluation. So the first heuristic, well, let me just step back for a second. So these heuristics work in an iterative fashion, meaning we take the graph representation of the network and we go step by step, selecting a switch in the network or a router in the network, which is going to be the most cost-effective switch to upgrade subject to the constraints. So the first heuristic, the volume, is relatively straightforward. We iterate through the switches, and we select the switch that serves the most traffic volume relative to its cost to upgrade it. And recall, the cost to upgrade is a function of port density and other factors. And the traffic comes from the traffic estimates, again, which I'll get to in more detail a little bit later. The intuition behind the volume heuristic is that switches that handle lots of traffic may be more likely to reduce the number of hops that traffic is actually traversing because of the locality of the traffic to that switch. The degree heuristic is slightly different. Instead of we simply go iterate switch by switch and pick the switch that has the highest link degree relative to its cost. And the intuition behind this one is that it allows us to potentially partition the network into many cell blocks to improve the scalability for the waypoint enforcement constraint, which in this case might be VLANs, the number of VLANs supported. Okay, so I'm going to next jump into the evaluation, and then I'll give a demo of a prototype that we built and illustrate a part of the fault tolerance mechanisms. Sorry, just to put that in context. So with respect to the evaluation, we're looking at three key questions. We want to understand how much SDN can I get for my budget? So in other words, how many endpoints in the network can I control through the SDN programming interface for a certain budget, meaning the number of switches that I'm capable of upgrading. The second question will be, how does Panopticon affect network traffic? And then finally, we'll look at a comparison of the heuristics under a particularly sort of pessimistic set of assumptions. So the methodology that we use in our evaluation, it's actually quite similar to that of Seattle, if you're familiar with this paper. If not, we start by taking three real configuration level topologies from large campus enterprise networks. The largest of which is the one that we're going to be presenting results for here. It consists of 1,713 layer 2 and layer 3 switches and routers. Of those, 417 devices are part of the distribution network, and we're focusing, or we're limiting ourselves to upgrading only those 417 devices, mainly because we want to exclude devices like core routers, which are very specialized high-capacity devices for which today there exists really no sort of SDN drop-in replacement, although in the future we expect that there will be. And the access switches, we choose not to upgrade because of the problem that we sort of laid out at the beginning, that there are simply too many of them. And we can do better by actually upgrading in the distribution network. As I said, we have the configuration level data for these networks, and we know the link capacities as well. So on top of this topology, we use traffic estimates from a large enterprise network in the neighborhood somewhere here. And we begin by clustering endpoints in the topology and then assigning addresses from the packet level traces in a round-robin fashion that allows us to preserve prefix locality while projecting traffic loads onto the links of our network. And so this has a random component to it. Okay, so based on that methodology, let me dive into the first question that we wanted to understand. How much SDN can I get for my budget? So let me take you through this plot sort of step by step. So on the x-axis, we're looking at the number of switches and routers in the legacy network that we're upgrading to have SDN capability. And on the y-axis, we're looking at the percentage of all the ingress ports in the network. So these would be distribution switch ports that are facing access switches, and using that as the level of granularity of control of the traffic in our network. And 100% would mean that every single access switch has its traffic subject to the SDN Waypoint Enforcement. And 0 would naturally mean that we're basically where we started in the legacy network state. So each of these 5 lines represents a different set of parameters that we specify. And the key parameters that we're dealing with in this plot are the flow table entries and the number of VLANs supported in the hardware that we're dealing with. So the line here along the bottom represents a very pessimistic case where our SDN switches only support 1,000 flow table entries. And we're assuming 1,024 VLANs are supported in the enterprise switches in our network. And as you can see, in this particularly pessimistic case, when we've upgraded about 20 switches, we're at about 30% of the endpoints in the network that can be exposed through the SDN programming interface. So for that particularly pessimistic case, it's not so great necessarily. But if we go to maybe a more realistic assumption of 10,000 flow table entries, which you can buy today and is going to come down in cost over time, we can see that with just 5 distribution switches being upgraded, we can get 80% of the SDN ports handled by the routing state in this network. Now I want to make it very clear, we're not yet dealing with traffic. We're just trying to understand the constraint of VLANs and flow table entries and the ability to express the SDN policy in the network. We'll get to traffic in just a moment. Just to step back for 1 second, let me illustrate that the benefit that you get between these lines and this line is given by the jump in 10,000 to 100,000 flow table entries. So if we were to assume that in the next year 100,000 flow table entries is going to be the norm, then you start out significantly higher than you do today when maybe 10,000 is the norm. And assume a normal pattern.
Traffic.
Well, yes, so we assume sort of a normal distribution of traffic. So what that means is, yeah, instead of every possible set of communication partners exchanging traffic, we're only dealing with the communication partners for whom we have seen traffic exchanged in the traces. So you wouldn't expect necessarily in an enterprise network that the traffic patterns are all-to-all, and the traces are likewise not all-to-all, so we use the traffic patterns in the traces. This additional benefit here is contributed by the assumption of 4,000 VLANs. So if we had devices that supported maybe the theoretical maximum number of VLAN tags, we would actually be able to support the entire network routing state with just one big switch. Now naturally that says nothing about the traffic, but with respect to routing state, it's not too bad. Okay, so now let's see how Panopticon affects the traffic in the network. So let me just start out by saying this slide has a few different assumptions about the traffic. The first thing that we did is we took the LBNL traffic traces and we scaled up the traffic volumes so that in the original topology, assuming a shortest path routing, we're getting the most utilized link has 50% of its link capacity utilized. So the problem is that if you just take the traffic raw, it's quite low utilization and doesn't tell us very much about what happens in a more heavily utilized network. The second thing that we do is we double the number of endpoints. And the reason that we do this is we want to sort of play a hypothetical question. What if we wanted to support two different policies or two different traffic classes for traffic coming from an access switch in the network? We also assume that the switches that we upgrade can support 10,000 flow table entries. And we assume again that the legacy network can support 1,024 VLANs. So the x-axis in this case, we're going from 0 toward 100 upgraded switches out of the 417 possible distribution switches. And the left axis, we're looking at the percentage of the maximum link utilization, so the link that is most utilized, the percentage of its link utilization, which is this line, and then the number of SDN ports that we can handle in the network, which is the same metric that we were looking at the last slide, just this time with more traffic and more ports. So the first thing that we observe is that when you've upgraded about 6% of the distribution switches in your network, the path stretch, meaning the additional number of hops that packets have to traverse, goes below 50%, and the maximum link utilization, which is this curve here, is about 70%. So the most utilized link in the network is at 70%. And keeping in mind that we scaled the traffic up so that in the original routing, the most utilized link was 50% utilized. So this gives us a bit of confidence that a mechanism or a scheme like Panopticon should be able to handle traffic in the enterprise setting. So let's look at a particularly pessimistic case and compare how our algorithms do under the assumption of merely 1,000 flow table entries, keeping in mind that as time goes on, we expect there to be more support for more flow table capacity in SDN-capable devices. So we're looking at the flow table entries in isolation here. We've made sure that VLANs are not a scaling problem or are not the critical factor in our scaling. And we see that basically the volume heuristic approaches about 70% of all the available ports that we could expose through the SDN programming interface when we get to about 320 switches. So this is a significant fraction of the network, but we're really hammering ourselves with the assumption of very few flow table entries. And in addition to that, we're assuming an all-to-all communication pattern. So assuming totally, overblown communication demands and sort of particularly low flow table resources, it's still possible to recognize a significant portion of the endpoints in the network, sort of accommodating them through the SDN programming interface. But naturally, it's going to require more upgrades in the network. So I'd like to just take a moment and illustrate a demo that's based on a prototype that we built just to actually prove to ourselves that the mechanisms that we're describing here can be realized. And I think you can actually just use it as... Yeah. OK. So what I'm going to be showing is a demonstration, a packet level trace of the same kind of topology that we were looking at earlier. Within each of these cell blocks, we've built solitary confinement trees from every endpoint to the upgraded SDN switches. And what I'll be demonstrating is how we actually reuse the fault tolerance mechanisms of the spanning tree protocol in the legacy network to allow us to actually accommodate failures in a maybe even more graceful way than what would be possible with SDP alone. So I'm going to let the simulation run, and you're going to see packets being traversed between the endpoints. And this link is going to fail. And what's happened as soon as that link has failed is the OpenFlow switches in this case have been listening to the STP broadcasts, so the BDPUs signaling a link reconvergence. And what they've done is they've signaled to the controller that this reachability over this path is no longer possible, and they've recomputed a shortest path route between the endpoints that allows the traffic to be basically rerouted through the inter-switch mesh. So again, it's nothing particularly complex, but it helps us establish that the mechanisms are feasible and that, that it's actually possible to listen in on legacy protocols like that. So, yeah.
Lost the focus.
Yeah, it's okay. Okay, so in summary, so I've presented Panopticon, which is a network architecture to operate a hybrid or transitional network as a nearly fully deployed SDN, as well as a planning tool that allows us to determine how to integrate SDN technology into an existing SDN deployment. We have the demo. Yeah, thank you for your time, and I'd be happy to take any questions.
So have you compared it against a skilled human? You just left in the stuff that evaluates what you've done, and you have a human select which switches to upgrade, or which devices to upgrade. Have you done that test and see how well a human does compared to the heuristic?
That's a good question. Actually, so I have to admit we haven't done that. I would say an interesting direction to go along those lines is also to just see how it works with a random selection, just as a baseline. I'd like to emphasize, though, that the results that we get, so kind of like the optimistic results that show that with just 6% of the distribution network, you can accommodate the traffic and the forwarding state, we think is fairly supportive in itself, and maybe you can do better than that. But if 6% of your distribution network already gets you, like a full SDN or a nearly full SDN, then maybe it doesn't matter how you got there. It just matters that now you can reason about your network through this programmatic interface and get all your cool, consistent network updates. And
if you look at what it comes out with, does it look like you pick what to upgrade? If you
So let me. So if you recall the let me see if I can get the list of all the slides up here. Well, so you recall the big network blob figure. So that's just kind of a spring layout of a part of the large topology that we evaluated the architecture on. And when you look at the topology, naturally there are a few nodes that just kind of pop out at you because of their degree distribution, and you would think, well, if I had the port density and the backplane, fabric that could support the throughput at those switches, then yeah, these are probably the switches that I would want to upgrade. And that, in a sense, is kind of the intuition behind like the degree heuristic. So in a way, having a human just kind of eyeball it, it might not be that you do too much worse.
These will be the core switches, which you don't necessarily capable of.
Yeah. So one of the big questions is, does it make sense to run the evaluation with the assumption of upgrading core switches? And so we kind of did it both ways, and it turns out that so you only get better if you have hardware that can do what a core switch does, but naturally we don't have a way of reasoning about the cost of upgrading a huge core switch with something comparable in the SDN capable product line. And therefore, it's hard to do an apples-to-apples comparison. The other thing is the question of fault tolerance. If you upgrade, just a few large core devices, and one of them fails, are you better off or worse off than if you had upgraded, 30 or 40 distribution switches? I don't really know the answer to that, but I think it's a question that you would have to think about. And then there was one other point that hopefully I'll remember, and I'll try to come back to it. Yeah. Mm-hmm.
Okay, and this is probably not very feasible to answer, but I was just wondering, in real-world large networks, if an organization decides to upgrade to substantial, say, SDN deployments, then is it known how they go about this? How does anyone talk about this? I mean, do they say, okay, whatever this particular model is, we'll just throw those out and replace all of those, or is it something like, well, we'll start with this little test network here, which is what I would suspect?
It's a good question. We talked with a number of large-scale enterprise network operators to motivate some of the operational challenges in the work, and a lot of them didn't really. Well, first of all, only one had sort of any knowledge at all about sort of what programmable SDN was or is and could be. Some of them have heard of OpenFlow, but there are a lot of kind of nebulous ideas and misunderstandings about what you can actually achieve. So I don't think that there really is a good grasp on how to get a sort of a logically centralized principled network orchestration from a kind of heterogeneous hardware landscape. I think there's not.
So maybe more pragmatic answer is that most likely you would just deploy an island of contiguous island of open flow devices and use the trial.
Okay.
Yeah.
But then that will go back to sort of what we call the dual stack approach.
And it doesn't in itself, answer the question of then how do you operate the network?
Earlier in your talk, you said that edge-based approach doesn't work for enterprise networks because where's the edge?
Mm-hmm.
So is that correct to assume that in enterprise networks, the IT department has control over all the endpoints or not?
So I'm sure that it differs, location by location. But in the network that we evaluated on, they did in fact manage access control policy lists at access switches, which we could observe by looking through the configuration data. And there was, there was actual, human sort of intervention, assigning VLAN IDs to separate traffic at the access switch level. So in a sense, there's evidence to show that currently operators are touching the edge. Actually, the point that I wanted to get to was that, one of the biggest challenges is not necessarily the configuration of these core switches, but just managing, at a human scale, what is the configuration state, what's the intended behavior of the network over the entire network, and actually maintaining a consistent view of that. In fact, one of the places we talked to, they had one guy whose job it was to basically keep the configuration state of 1,500 devices in his head, which is a lot of configuration state in my mind.
So my question is this software upgrade to the endpost machines an alternative or not?
It may be possible for some networks, depending upon the hardware that they have deployed, but in 2 of the networks where we did on-site visits, the majority of the access switches would not be capable of having a firmware upgrade solution.
No, not the access switch, but the endpost itself, the machine.
Ah, okay. So you're talking about putting like a Vswitch on a user's machine and managing that?
Any form of programmability.
Yes, so it raises the question, where do you try to place the boundary of your network, and do you have a trusted, sort of edge? Yeah, okay. So I understand your question. I would.
So in terms of hardware costs, that's zero cost.
In terms of hardware costs, it's not zero, because you actually have to enforce that every user of the network actually is running the correct software, and this is a really non-trivial problem. One of the network operators that we spoke with actually tries to do this by verifying, from the bootloader up, the configuration of the systems that get put in their network, and it's just a colossal failure.
Some idea of how hard that would be to do at ICSI, which is so far away from an enterprise network, so it's almost impossible to imagine on a true heterogeneous enterprise network. You've got old database servers for running IBM hardware from 30 years ago in most places, and you're not upgrading their network stacks.
It's not inconceivable, though, that as more and more sort of mobile devices that are kind of, where you don't have root on them, where Google or Apple or whomever, Microsoft controls the kernel and everything, below and above, they could choose to expose, a Vswitch through some kind of authenticated channel. But we didn't really, go in that direction in this work. We're more motivated by the scenario of a network like a university campus or a large corporate organization with sort of a heterogeneous client, you know, landscape.
There's one of our network nodes above your head. Try and update its stack.
Okay, but I would, basically the work that you're describing in terms of, there is a work that advocates putting in all that functionality in the edge, basically extending the end-to-end. The thing is that where your trust boundaries are, that decides where that functionality resides. You don't trust, you can't even mess with that, or you can put a box, gateway, in front of it. The point that this talk made was that there are lots of endpoints. It's invisible to do that. And the way I think about it is that you're trying to be as close as possible to the edge, because that would minimize the path stretch. The stretch you have to take to basically get out of the actual path this traffic was thinking. So at the end, we would like to have basically to push this state as close as possible to the endpoints. That would be the most scalable solution. You had another point, which I don't quite agree with. Is basically the more boxes we deploy, we upgrade. You get the benefits of traffic engineering and so on and so forth.
So like the fidelity of, you know, what the control platform sees becomes higher. I mean, this is,
the question there would be, why an end-to-end traffic engineering approach, basically using path diversity, doesn't play equal?
Let me give you an example. So let's say that you did actually push, you know, the SDN programming interface fully to the edge, and you wanted to be able to do you know, fine-grained control of, you know, flow-level routing inside the network. So inside the network, you still rely upon whatever legacy routing control interface you have. Now, if what exists in your network, let's say you have, you know, I don't know, some equal cost multipath or even some really fancy non-equal cost multipath, then maybe that's good enough for you. But the point is, as you begin to actually upgrade and put SDN devices in the network and build the inter-switch mesh up and expose a higher fidelity view of the SDN topology to the control platform, you get that kind of for free. You get, you know, path diversity, and you can deal with that through the same SDN programming interface that you do with, you know, the access control list, and you do with, you know, the middle box rerouting potentially. So the goal is to think about how can we expose the network as an SDN, and not how can we get part of the network under control of, you know, of an SDN. And
The thing is that either you have the feature to do multi-path routing or not. SDN by itself doesn't add that feature. It just exposes the interface for you to use that feature. So either your fabric supported that feature in the first place, in which case the traditional routing protocols might have used it as well, or you don't have it. Just adding a programmable stack doesn't...
I mean, I would disagree to an extent, because, I mean, imagine, you know, you have a large, you know, let's say you have a large Ethernet deployment, where, and this is actually the case in many large campus networks, they have large Ethernet islands, you know, that are just broadcast domains that maybe they split up with a few different spanning trees, and then they have, they want to be able to make use of multipath to improve, you know, throughput between whatever, who knows what applications may be running. And the point is that in that kind of environment, having the SDN programming interface to be able to manipulate flow table level forwarding state and achieve multipath over, you know, the Ethernet, existing Ethernet topology is something that you wouldn't necessarily have, and it is something, you know, without the SDN, or you would have to introduce Trill or some other kind of, you know, overlay mechanism. But I would actually try to caution against thinking about the problem of multipath as, I mean, it's kind of like, I don't want to say it's a side note, but it's kind of, it's not the main emphasis in my opinion, or kind of the main goal.
But that was traffic, is there anything besides traffic engineering that incremental deployment buys you? Because you said some policies are enforceable end-to-end, some policies are not, like traffic engineering. So any other examples?
Besides load balancing?
Any form of traffic engineering in QoS?
Well, I mean, in some sense, yeah. Think about
looking for those examples.
Yeah. So one example would be, the granularity at which you can do, for example, consistent network updates. I mean, if you're familiar with the Wright-Blatt paper on abstract, yeah, sure. So the basic principle is that you go and you upgrade the forwarding state in a kind of two-phase lockstep, two-phase commit fashion, and the degree of control over the network that you have as you upgrade more forwarding elements to support the SDN programming interface, which gives you the ability to do that consistent network update, means that now you can do more types of updates in a consistent fashion. I mean, I don't know.
I will continue this offline.
Okay, but yeah. Okay. Sure. So I certainly agree with your point that, on the one hand, if you look at the question of can you get control, where do you draw your trust boundaries? That influences, the design choices that you would make in trying to deploy a system like this. But yeah, sure, we can talk offline about that.
Any other questions at this point? That was a great discussion.
Yeah, thanks everybody.
Thank you.
All right, thanks.